Okay. Hello, everybody, and good afternoon. My name is Mehri, and I'm a senior lecturer in the School of Civil and Environmental Engineering at UNSW. And my apology that I couldn't attend the presentation in person. So hopefully I can convey my message and the content of my presentation remotely. The title of my presentation is related to the data-driven approaches for indirect structural health monitoring, or so-called drive-by bridge inspection. So as probably everybody in the lecture room knows, we are facing with a great challenge related to the deteriorated road infrastructure, in particular bridges. And according to the literature, 72% of bridges in Australia have been constructed before 1976, and basically they are considered already defective. And another challenge that we are facing is that basically the budget of the road authorities is limited, and the current practice for maintaining the safety of this road infrastructure is mostly relying on visual inspection, which is happening based on some intervals, which, as you can imagine, it doesn't provide real-time information about the health state of the bridge. So the current practice to basically monitor the safety of the infrastructure is either through the NDT-based approaches or conventional structural health monitoring approaches. And both of these techniques, although have got to a mature stage, but they are very costly, and probably deployment of such systems on large scale structures is basically not cost effective and requires a lot of time, a lot of labor works. And not only that, the maintenance of the system is a big issue, because usually the life of the sensory time, the sensing system data acquisitions is less than the lifetime of the structure itself. And another challenge that we are facing with the conventional structural health monitoring approaches is that the transmission of the huge amount of data that are collected in real time is a big challenge. For example, in the Sydney Harbour Bridge project, that we have around 2,000 accelerometer sensors on the bus lane. Under the bus lane, we are collecting data in a high sampling frequency, and storing all the data, transmission of all data, that's a big challenge. So now the question is that what other approach we have in order to deal with this problem that we are facing. So recently there is a new paradigm in the field of structural health monitoring, which is called indirect structural health monitoring, or people also name it as drive-by bridge inspection technology. And the idea behind this technique is that if we have a bridge structure, and this bridge structure basically has a problem or a crack or some sort of deterioration, what if we use a passing vehicle as a sensor, and we try to extract information about the health state of the bridge, instead of looking at sensors installed on the structure of the bridge, but using sensor installed on the moving vehicle. So in other words, we try to identify information about the state of the bridge purely based on the response of the moving vehicle which pass over the bridge. But you may ask why the vehicle should have information. The reason is that when the vehicle passes over the bridge, there is a dynamic interaction between the vehicle and the bridge, and basically the vehicle acts like a substructure as part of that big superstructure. And therefore, by collecting the dynamic response of the vehicle, like the acceleration response, displacement response, contact point response, or even the axial force, it is possible to extract information about the characteristic of the bridge without using any sensor on the structure of the bridge. And if we move in this direction, then we try to answer basically mostly the first two levels of the structural health monitoring questions. The first level is that whether there is any damage in the structure of the bridge, and second, localization of damage. Basically, these two levels at the moment are the research focus of my research group at UNSW in the School of Civil and Environmental Engineering. And we are trying to basically develop algorithms and frameworks that purely based on the response of the moving vehicle answer the question of the detection of damage and localization of damage. So according to the literature, basically this idea was first initiated by Professor Y.B. Yang in 2004 when he published the first article in this area in sound and vibration. And after that, a large number of researchers across the world started working in this direction. And people basically have used the simplest one is just purely a moving load, then a quarter car model or half car model, and even in many of the recent publications, people are using much more complicated vehicle models, using 3D models, considering a larger number of degrees of freedom. But the thing is that in many of these applications and previous publication, it has been shown that yes, it is possible to extract the first few natural frequencies, mode shapes, and even in some studies, the damping information of the bridge purely based on the response of the moving vehicle. Therefore, the analytical and the closed form solution and the basically investigations based on the numerical approach like finite element kind of shows to us that it is possible to extract information from the moving vehicle without putting any sensor on the structure of the bridge. And that's something that basically I'm focusing on, and I want to extend it to next levels and basically experimentally and in field, we validate that, yes, it is possible, and if not, how we can improve the performance of the sensing vehicle that basically is acting as like a mobile sensor. So as you can imagine, there are a lot of challenges with application of this technique for bridge monitoring. One of the most important challenges that we are facing is related to the road roughness and on a smoothness surface of the road, because that introduced a lot of frequencies in the response of the vehicle which don't associate with any of the bridge frequencies. Measurement noise, environmental variation, and basically variability in the vehicle parameters all can contribute to the basically uncertainty in the results. And finally, basically the characteristic of the vehicle have a big impact on the performance of the drive-by bridge inspection. And in addition to that, the effect of the passing traffic and basically damping of the vehicle is all affects significantly on the VBI response that we are getting through the basically vehicle. However, in the literature, people have proposed solutions in order to overcome some of these problems. For example, for road roughness, people are using multiple axles and try to subtract the axle responses with a time shift, because we know that both axles pass through the same road roughness. Or in terms of the basically vehicle frequencies that basically blur the effect of the bridge frequencies, people use vehicles with higher level of damping, or people use laser-based measurement in order to measure the contact point response. However, in the approach that basically I am following in my research group is mostly relied on application of data-driven frameworks in order to basically solve this problem and approach the problem from data-driven approach or angle, basically. As you probably know, the data-driven approaches can be classified either as supervised or unsupervised learning. And this application of supervised learning for structural monitoring problems has been proved not practical. The most important reason is that we usually do not have access to information from damaged state of the structure, because in order to train a supervised learning model, we need to have access to labeled data, but that's something that we always lack in practical application. And further, it's too costly to train a supervised learning model, too expensive, and it's not really transferable to other bridge estate or other bridge models. Therefore, my approach in order to tackle this problem is purely based on unsupervised learning. During the last 2 years that we started working on this project, we have made quite a lot of progress. First, we started with clustering-based approaches 2 years ago, and basically the response that we are getting from the vehicle is purely based on the time series response. And it is very important that we extract meaningful information from this time response, and in addition to that, reduce the dimensionality of this, large time response that we have from the response of the moving vehicle. So the first algorithm that we developed, and we did a lot of investigation on this, was an algorithm that in abbreviation we call it UMAP. And UMAP proved to work, as I will shortly show some of the results. So the idea behind UMAP is that it's basically a projection from high dimensional space to lower dimensional space, with the aim that extract the most amount of information from a given time response. But then we realized that in order to apply clustering-based frameworks, it is required that you have access to basically a response of the structure, response of the vehicle from multiple states, because most of the time these clustering algorithms, the aim is that we are going to group the data based on their similarity in order to kind of say that, look, these responses that I have collected correspond to 3 different clusters, and each cluster potentially correspond to a different bridge state. So we found that although the approach worked very well in our experimental data, but because of its limitation, we try to work on an approach that doesn't require all the data to be available basically in one hand in order to use the approach. Then we shifted to application of deep learning based methods, and we used adversarial-based techniques, and we started with just purely adversarial autoencoder, and then we extended to a stacked autoencoder, and finally we realized that amongst all the existing autoencoder-based or deep learning-based methods, the adversarial autoencoder, which is a very, very new variant of the technique developed 2-3 years ago, works extremely well compared to the competing techniques. And I will again show the results of this technique very soon. But again, application of deep learning has another challenge. The reason is that usually in order to use deep learning-based techniques to tackle the problem, we require a large number of data sets in order to train your model. And that may not be something practically available, to collect a large number of data sets. Then, just very recently, maybe a couple of months ago, we have started investigating application of time series-based methods. And in particular, we are looking at a method called matrix profiling, which the method aims to identify motifs and repetitive patterns in time series response that we are collecting from the vehicle, with the aim to identify any outlier and basically segment the time series into sections that each section corresponds to a different context, or in our case, it's going to be a different bridge state. So in the next couple of slides, I'm going to go through the results that we have from these 3 different approaches that we have investigated for both our numerical and experimental cases. So basically, we started with a half-car model, numerical model, and all the details of this work can be found in our publication in our MSSP paper published in 2022. And we applied the clustering technique that I mentioned to you. So we investigated 5 different states and purely unsupervised And we realized that UMAP successfully clustered the data into 6 clusters. However, PCA, which is very much well known for its strong capability in dimensionality reduction and keeping the variance of data, it failed to do so. And then adversarial autoencoder also successfully distinguished different bridge states from one another, where PCA failed to do that. And this is the matrix profile that I have basically concatenated the time response of the vehicle passing through 2 different stages of the states of the bridge. And as you clearly see, matrix profile performed extremely well in order to identify the time instant that the state of the bridge basically changes. And later, in collaboration with Kyoto University in Japan, we did a lot of experiments, and basically we changed experimentally the state of the bridge by adding a stiffener place or adding a mass. And we collected the acceleration response of the vehicle and did a lot of frequency-based studies. And again, the techniques that we initially applied on the numerical model proved to work and basically distinguish different states of the bridge from one another. So moving forward now, the next step that we are going to focus is going to be the basically application of the frameworks that we have investigated previously in the field. And to this aim, during the last 2 years, in collaboration with the Mechatronic School at UNSW, we have made a fully customized electronic car. And this car is equipped with so many sensors. And the good thing about this car is that we have capability to change any dynamic characteristics of this vehicle, the suspension, the mass, axle distance, and because it's fully autonomous, we have control to keep its speed fully constant, which is another challenge in the context of drive-by bridge inspection. And each time we can calibrate it using modal analysis. And the next step is that we are going to basically artificially create some damages on real-world bridge and test the performance of the 3 algorithms that I showed using this test car. And at the end, I would like to thank ARC for provision of support for this project in the form of DECRA, and also JSPS for all the support for helping me to do the experiments at Kyoto University. Thank you so much, and I'm happy to answer any questions if you have.
Thank you, Mehri. Thanks so much. We have time just maybe for 2 questions, I think. John.
Hello, Mehri. Can you hear me?
Yes, I can hear you, Jianchun.
Mehri, is excellent work and quite impressive, particularly from the technical side. Actually, I have a question, a little bit fundamental, may not exactly expecting answer, but we probably need to think about it. As I mentioned in my presentation, damage detection has been already long ago recognized is not deterministic inverse problem. Currently, your fundamentals still treat it as deterministic with inverse problem. I think that can be a bit issue. Let me elaborate a little bit. For example, if you have boundary condition changes, for example, supporting change, or the size, partial of the damage change, anything, it's very hard for your approach to pick it up. And those things is sometimes not certain yet. It's a lot of uncertainty there. So your technique is very valuable because you showed how if the question can be determined, you can pick up things, use different technique. But the fundamental of the damage, particularly those local damage, I mean, it is not deterministic inverse problem. So I think we probably can talk to each other later on. It's really the, existing sensors are useful. Your technique driving vehicle, moving sensor, very useful. I think solution has to be combined. That's my comments on the question.
Do you want to comment on that, Mehri?
Yeah, thank you so much, Jianchun. Really appreciate. So I absolutely agree that this is not a deterministic problem, and that's the reason that we are using data-driven approaches rather than this approach. The reason is that when you use data-driven approach based, you are taking into account all the uncertainties that we may have in the different runs of the vehicle when it passes over the bridge. And that's the reason that basically we are moving with this data-driven framework. But I absolutely agree with your comment that it's not a simple inverse problem.
Thank you. Any other? Yeah. Okay, Ronald.
All right, thank you, Mehri, for great presentation. I'm just curious if you kind of having any plan to like implement a model-based methods for the detection, because from what I can see there, you can actually get the mode shape from your measurement, because when you move in the vehicle along the bridge, you get the data up on the point of the bridge. So it will be possible to get the mode shape of the bridge. So maybe that would be your concern on futures.
Actually, as I said, application of mode shape based features that are purely extracted from the response of moving vehicle has been something that has been addressed already in the literature. But that's not going to be the way that I am looking at the problem. The reason, and I think part of your question was that whether or not I'm going to use any model-based approach, and the answer is no. The reason is that I noticed that because I have worked on several large-scale bridges in the past, and I noticed that establishing a reliable finite element model of a large-scale bridge, which has, I don't know, maybe 50, 60 years old, is something that's quite challenging, and probably is, establishing that model, validating, updating that model is something that is not easy and practical. So that's the reason that I'm kind of getting away from model-based and physics-based approaches.
Thank you, Mehri. Okay, we need to move on. Well done on a lovely talk. Thank you.